Welcome to 7.6 Rational Parent Function. Today we are going to graph and transform the rational parent function. So the first thing we have to do is talk about what does the parent function look like. So it is also known as the reciprocal function, and it takes the form 1 over x. And remember, anytime I have a fraction, I will have undefined values, and in this case x cannot equal 0. There are two important things that we have to take into consideration when we are graphing rational functions, and that is our vertical asymptotes and our horizontal asymptotes. So let's go ahead and talk about vertical ones first. So it's a vertical line that the graph approaches as the value of y becomes extremely small. So as it goes out to the ends. And one thing you have to remember and you have to note about vertical asymptotes is we can never cross them. And it is a vertical line. So whenever I am asked to identify the vertical asymptote, it is going to be written in an equation. So notice here, I have a vertical asymptote at x equals -2, and my graph is never going to cross that line. It's going to get really close, but it will never go over. And then for my horizontal asymptotes, they are very similar. It is a horizontal line that the graph approaches as the x values become extremely small or large. The only difference is you are able to cross these graphs. So you may dip under it, you may dip above it, but really you're just getting closer to this line with the potential possibility to cross it. And again, it's a line, so we're going to call this a y equals a value. In our case of our example, the horizontal asymptote is at y equals 4. And another name for horizontal asymptotes is end behavior. The reason why we call it end behavior is because it's not functioning exactly like the vertical asymptote. We can cross it, but what is your graph doing as it gets to its ends, as we go to negative infinity and as we eventually go to positive infinity? So let's graph the parent function. So first we're going to introduce a table of values. I have my function f of x is equal to 1 over x, and I'm just going to plug in these x values into the denominator. So I'm going to get 1 over -5. I'm going to get 1 over -2, 1 over -1, which is just -1. And then we come to a special case, our fractions. And this is kind of nice because we've already dealt with dividing a fraction by a fraction. This is one of those instances where we're going to keep, change, flip. So I would keep 1, change this to multiplication, flip -1/2. So basically I'm doing 1 times -2, which is just -2. And then I have 1 over 0. And remember, we cannot divide by 0, so this is undefined. And I get similar values on the other side, just positive 2, 1, 1/2, and 1/5. Something that you should be noticing is as my x values are getting bigger, my y values are starting to get smaller in both directions. So the first thing I'm going to do is plot my points. So I have all 8 points here on my graph. Remember, I'm not going to get a point for x equals 0 because it is undefined. And then I'm going to start moving into vertical asymptotes. So a vertical asymptote is going to occur where x is undefined. And for us, x is undefined at 0. So that is where my vertical line is, meaning I cannot cross this line whatsoever. Now, horizontal asymptotes are a little bit different. It's because it is dependent on what y value is your ends of your graph approaching. So if I look at my graph and if I were to fill in and connect my points, and that's something that you do not want to forget. You want to make sure that you actually go in and connect them because you will be surprised how often that gets forgotten. If I follow along the trend of my data points, I'm going to get my values really, really close to the line y equals 0 in both directions. So as my ends of my graph start to even out, they're evening out to 0. So horizontal asymptote is y equals 0. Now, for domain is going to be all real numbers except where I have my vertical asymptotes. So for this one, it's going to be negative infinity to 0, union 0 to infinity. And the same thing goes for my range with my horizontal asymptotes. It's going to be everywhere but that horizontal asymptote. So negative infinity to 0, union 0 to infinity. Now let's go ahead and graph a rational function with transformations. So one quick reminder of transformations. I have, if a negative is in front, it's a reflection over the x-axis. Anything inside the actual function, which this minus h is going to be a shift left, right. We are going to do the opposite of what it seems to be. So if I get -2, I'm really going right to. Plus k is my shift up down, and I have an a in the numerator, and that's going to be a vertical stretch. If I were to have an a in the denominator, that would be a vertical compression. But more often than not, you're going to be seeing vertical stretches over vertical compressions for rational functions. So let's go ahead and look at my graph. I have 1 over x minus 2 plus 3. So the first thing I notice is this -2. That means that my graph is going to shift to the right 2. Because remember, I'm doing the opposite. The next thing I notice is the +3, which means my graph is shifting up 3. It's going to do exactly what it looks like. And the nice thing about just graphing a rational function based on the parent of this form is all we have to do for shifts is just move the asymptotes. So remember, I have an asymptote at x equals 0 and y equals 0. I'm going to move those based on the shifts that I have here. So my vertical asymptote is going to move right 2. Now it's sitting at x equals 2. My horizontal asymptote is going to move up 3. Now it's sitting at y equals 3. And something to note for the sake of quizzes and tests in this class, there's only two points that we are requiring you graph for these types of functions. And it is this key point here, typically right 1, up 1, left 1, down 1. Those are the only two we need on graphs like these. So right 1, up 1, left 1, down 1. And then, of course, do not forget to connect your dots. We only have one, but the general shape is going to be the same as long as you don't have any stretches or any reflections. Just draw it as if it were to look just like the parent function in the same direction as the parent function. Now, domain is going to be based on my vertical asymptote. It's going to go from negative infinity to 2, skipping over 2 because remember, I cannot cross this line. And the range is going to go from negative infinity to 3, skipping over 3, continuing on to positive infinity. Looking at example 2, we're identifying the transformation used to get from f of x to g of x. So first thing I notice is my numerator changed from a 1 to a 2. Well, that indicates that a vertical stretch of 2 occurred. I then notice my denominator changed from an x to an x minus 2, which means I went to the right 2. And my -2 and +4 changes. Remember, if you have a -2 here, that means you're starting at y equals -2 and you're ending up at y equals +4. So in order to get from -2 to +4, I have to go up 6. And these are my 3 transformations from f of x to g of x. So let's go ahead and graph one more time. I have my function f of x. I have a shift left right, a shift up down, but I'm also noticing a reflection. I have a reflection over the x axis. I have a shift to the left 2, and I have a shift down 4. Remember, anytime we are graphing, we're always going to apply our shifts left, right, and up, down first. So my vertical asymptote is going to move to the left 2. There we go. And my horizontal asymptote, and I already went and wrote my domain because if I know my vertical asymptotes, I know what my domain is going to be. My horizontal asymptotes are going to move down 4, y equals -4. I get negative infinity to -4, union -4 to infinity. Now, the reflection over the x-axis is new. So remember, if I were to go in and graph this as I would a parent function, I would come in, I would go right 1 from my new origin, up 1. This would be my first dot, and I would draw my curve. Now, I have to remember that things are reflecting over the x-axis. So this piece that would normally be here is going to flip and be down here. Similarly, I would normally have a piece here with this point indicated left 1, down 1. But because of the reflection, it's now reflected up because this new horizontal asymptote is functioning as my new x-axis. So that takes care of the reflection. I have my domain, I have my range. For example 4, we are going to create a rational function that would have a domain of -infinity to 6, union 6 to infinity, and a range of -infinity to 4, union 4 to infinity. Well, one thing to note is domains are going to be based on vertical asymptotes, and range is going to be based on horizontal asymptotes. So if I have a hole at 6 in my domain, that means there's a vertical asymptote at x equals 6. Similarly, if I have a hole in my range at 4, that means I have a horizontal asymptote of y equals 4. And then from here, all we have to remember is that our shifts left right tell us where our vertical asymptotes and horizontal asymptotes end up being. So if I'm at x equals 6, that means I moved right 6 from the parent function. And if I have a horizontal asymptote at y equals 4, that means my graph from the parent function went up 4. And then all I have to do is take these and apply them to a rational function. So I get y is equal to 1 over x minus 6. Be careful here because we're going to have to write the opposite of what we would think when we see right 6. And I have plus 4 to shift it up 4. And of course, you could add a little spice to it. You could reflect it. You could give it a vertical stretch or a vertical compression. Just be careful to include parentheses. But the baseline function is enough to correctly answer the question. Another thing I want to note, it asks for a function, meaning you have to have y equals or f of x equals, something indicating that this is a function and not just an expression. For example 5, we are going to use our knowledge of transformations to identify which functions below would cross the x-axis, the y-axis, both or neither. So one thing we have to recall is that the parent function has a vertical asymptote at x equals 0, which is the y-axis, and a horizontal asymptote at y equals 0, which is the x-axis. So if I were to quickly sketch myself a rational parent function, I'm going to have a vertical asymptote sitting on the y-axis. I'm going to have a horizontal one sitting on the x-axis, and I would have my curve kind of in here. Now, I want to know what transformations are going to cause my curve to move over to potentially have a y-intercept or move down and potentially have an x-intercept. Well, remember, if we're moving these asymptotes, we are moving these curves. So if I want to cross the x-axis from the parent function, I need to be moving my graph up, down. And if I want to cross the y-axis, I need to be moving left, right. So up, down will create x-intercepts. Notice how it's crossing my x-axis. And left, right will create y-intercepts as it crosses my y-axis. So let's go ahead and identify the transformations for each of these graphs. So my first one is going to have a reflection over the x-axis with a vertical stretch of 2. The second one is moving left 2. The third one is just having a vertical stretch of 8. And the fourth one is moving right 3, up 1. So remember, we're looking for up, down, or left, right. If I look at my first one, It doesn't have any of that happening. Yes, this is going to get a little skinnier. Yes, it may show up down here, but it's not going to cross either of them. So this is a neither. This one is moving to the left too. So this vertical asymptote's moving to the left too, which means I'm going to end up with a y-axis cross. Vertical stretch of 8, again, we are coming into that territory of yes, this is going to get skinnier, but it's not going to change the fact that I cannot cross the y-axis and I cannot cross the x-axis. So this one is neither. And then for my last one, I am moving to the right 3 and I'm moving up 1, which puts my curves sitting over here, potentially more over here. So I will end up with a y-intercept and an x-intercept. So that's going to give me both.